In our first question here, we are identifying experiment, sample space, and our event of interest. So we spin a spinner 2 times and we hope to get the same color. That's going to refer to our event of interest. So the experiment here is spinning the spinner 2 times. So that's what you do to collect your data. And then the sample space is going to be the set of all possible outcomes. So in this case here, we've got on our first spin, we can get red, blue, green, or yellow. And then our second spin, we can also get red, blue, green, or yellow. So we can form this outcome table and get all our possible outcomes. So red and red, red and red, red and blue. So red first, blue second, red and green, red and then yellow, blue and then red, and keep going all the way down until our last one is yellow and yellow. So that's the list of all the outcomes. And then our sample space, that's the set of all outcomes. So the sample space we denote with capital S, and that's the set of all outcomes. So starting with red, red, and then red, blue, and then going all the way down to the yellow, yellow. So 16 outcomes there, 4 times 4. And then our event of interest is that we get the same color. So let's call that event E. So if they're the same color, that could be your red, red. Along this diagonal, this would be blue, blue there. And then here will be green, green. And then yellow, yellow. So all of these 4. That's our event of interest. So red, red, blue, blue, green, green, and yellow, yellow. And this is an equally likely sample space because each of these outcomes here is equally likely as are each of these. 1/4 probability each way. Cards drawn from a well-shuffled deck of 52. Find the probability the card is. So it might be helpful to actually look at a deck of cards here. So there is our deck of cards. And then we are going to draw a card, so just one card. We want to know what's the probability it's a club. So the clubs are here. There's 4 suits with 13 cards each. So 13 clubs, and then 4 times 13 is 52. So 13 clubs out of 52 cards right there, A. A black or an ace, so or there. Or unites the 2 sets. So the black cards are here and here. And then aces, let me do that in a different color, are here. So we're going to keep the 13 and 13, 26 black cards. The 2 black aces are already included, and then plus 2 more. So 26 plus 2, 28 out of 52, which is D. So that's one way to do that. Or you could use actually the union rule. So 28 out of 52. A diamond or a black card. So diamonds are here. Or a black card. So our black cards are here, spades and clubs. Now there's no overlap between these, so we're just going to count them up. We've got 1, 2, 3 times 13, which is 39, because OR keeps everything, unites the 2 sets. So that will be 39 out of 52, C. a black diamond. So the diamonds are right here. And we want to know how many black diamonds are there. Well, none. All the diamonds are red. So that's an impossible outcome here. So that's going to be 0. Not an ace. So the aces are here, 4 out of 52. If you're not an ace, you're going to be the total minus those 4. So this will be 52 cards total minus the 4 aces out of 52. So desired out of total outcomes. 48 out of 52. Right there. So all of these you can do with desired out of total just looking at a deck of cards. You don't have to use the rules. Sometimes it will be helpful to use the rules, like the union rule here. And then in number 3 here, we've got a table, shows the number of people have a certain disease given their alcohol consumption. So we've got drinker versus non-drinker, number that have cirrhosis, liver cancer, and heart attack. And so we're trying to analyze and see if there's any patterns here. So first we want to know if a person is selected at random, find the following probabilities. So we've got 95 total. We've got 82 is the total of drinkers, 13 is the total of non-drinkers, total cirrhosis 60, total liver cancer 26, total that had a heart attack 9, and then if you add this row or add this column, you get 95 total. So that's our grand total. So a person is a non-drinker. Well, non-drinkers are 13 desired outcome out of our total of 95 total outcomes. So 13 out of 95 desired out of total. Because it's an equally likely sample space. We're selecting one person at random, so it's equally likely that we would select any of those 95 people. A person is a non-drinker and has cirrhosis. So non-drinkers are here. People that had cirrhosis here. And is the overlap. 3 is circled twice. 3 is in the column and in the row. So it's going to be 3 out of the 95. So again, desired out of total, 3 out of 95. Didn't need formulas on that one. Person is a drinker or has had liver cancer. So our drinkers are here, this first row. That's 82. Liver cancer is the second column. That's 26. Or puts things together. So you're going to add this row, add this column, and then the 22 got counted twice. So we can do this. Let me do this. So let's see, we had 82 was our total drinkers, plus 26 is our total had liver cancer. But then that 22 got counted twice. So we subtract out the things that are counted twice, and then out of total outcomes of 95. So, and if you do the calculator work there, you'll get 86 out of 95. And again, this is the union rule that we're using there. Probability of A union B. You do probability of A plus probability of B, and then minus probability of the overlap, A and B. Remember, union is or, and the upside down U is and. So probability of A right here, 82 out of 95, plus probability of B, 26 out of 95, and then minus the 22 out of 95 overlap. What's the probability the person has a heart attack if we know, keywords, they're a drinker. So if we know is telling us that's a conditional probability, that's a given condition. So that restricts our total outcomes. So this is going to be total outcomes are we know they're a drinker. So we know that they are in this row here, which is 82. And then out of those 82, how many had heart attack? And that is 3. So 3 out of 82. So this will be 3 out of 82. This is the drinkers. And then this is the heart attack. Just from the drinkers, because it's given they're a drinker. Person is a drinker given that. So again, that's conditional probability. They have liver cancer. So liver cancer is given. That's your total outcomes. So on the bottom, our total for liver cancer here, that column is 26. And so our total outcomes down here are 26. And then out of those 26, we want to know how many are drinkers. Well, 22 here are in the drinker column. So this will be 22 out of 26. So on the bottom here again, this is liver cancer. And then this is drinkers from liver cancer, because it's given you're starting with liver cancer. Are the events H and D independent? So H is heart attack and D is drinker. So are they independent of each other? Do they have an effect on each other? And then are H and D mutually exclusive? So mutually exclusive, let's do that one first. Mutually exclusive means separate. They are not separate here because they have an overlap of 3. So that's actually the easier one to answer. So are they exclusive? No, because they overlap. There is someone who is both a drinker and has had a heart attack. And then to look at independent, you have to compare the probability of H, see what that is, versus the probability of H given D. So see if it makes any difference having one event given. So heart attack is desired out of total. We had 9 heart attacks out of 95 total. And then H given D, so if we just restrict ourselves to drinkers, which is 82 total. And then we want to know out of those 82, how many had heart attack? And in that first row, 3. So 3 out of 82. And these are not equal. So if it's given they're a drinker, that does have an effect. So are they independent? No. And this is your explanation, is that being given drinker has an effect. Number 4, here we're given 50.5% of the U.S. population is male. Incidence of heart disease in men is 7%, 4% in women. So yeah, women usually start heart disease about 10 years later than men. We want to determine the probability a random adult in the U.S. will have heart disease. So we're going to set up a tree diagram. So let's define our events here. Let's let H be the event that they have heart disease. And let's let M be the event that they're male. So we first want to do the male-female split because this is 7% of men and 4% of women. So those are conditional probabilities. So we got our male, and then not male is female. So, and then we had 0.505. Boys are born a little bit more frequently. It's not quite 50-50. And then that leaves 495 for the women. So 1 minus 0.505. And then for the males, they could either have a heart attack or none. Or, I'm sorry, heart disease or none. So not heart disease. Females, heart disease or not heart disease. And then put those probabilities of 7% heart disease in men. So given that you're male, this is 0.07. And then 1 minus 0.07 is 0.93. Remember, they always have to add to 1 on the branch. And then if you're female, it's 4%. So heart disease here will be 0.04. 1 minus 0.04, 0.96. So male heart disease, MH, that's one outcome. Male and no heart disease, MH bar. Female heart disease, FH. Remember, bar is our complement. And then female no heart disease, F, H bar. So then we multiply along the branches. So 0.505 times 0.07, 0.505, 0.93, 495, 0.04, and then 495.96. And then if you do the calculator work on these to 2 decimal places here, you'll get 0.04 for the first one, 0.47, 0.02, and 0.48. And if you add all these up, you get 1.01, a little bit of round off error, but you should get 1. So now we can start answering questions. What's the probability a random adult is male and has heart disease? So that's right here, male and heart disease. These are and probabilities. So 0.04, that's MH. Probability is male and does not have heart disease. So male, no heart disease, 0.47. So this is MH bar, 0.47. Not male, but has heart disease. So that's female heart disease, 0.02. Not male, not heart disease. So that's female, no heart disease, 0.48. So that's FH bar, 0.48. And last question, probability of random adult has heart disease. So that's probability of H, heart disease. Well, there's 2 ways you can have heart disease. Either be a male and have heart disease, 4%, or female and have heart disease, 2%. So this is going to be probability of male heart disease or plus probability female heart disease. So that's 0.04 plus 0.02, which is 0.06. All right, and then let's see, we're looking at discrete and continuous random variables, number of customers that order at Wendy's drive-thru in a 30-minute period. So this one's going to be discrete because you can count it. It's going to be, 1 customer, 2 customers, 5 customers. So 1, 2, 3, ... You can actually count it. The time, so number of customers, that's discrete, time that passes between customers during a 30-minute period. So, well, if you had one customer at the beginning of the 30 minutes and one at the end, there would be 30 minutes between. Or there could be virtually almost no time between if it's like backed up and it's just customer after customer after customer. So this one's actually going to be continuous. It could be anything in the range of 0 to 30 minutes. So, oops, spelled that wrong there. Continuous. So this could be a whole range of values, 0 to 30 minutes. Not countable, because time is infinitely divisible. And then let's see, up next, consider the following probability distribution here. It says number of years a person with a transplanted heart survives. So 35% chance they survive 1 year, 22% chance they survive 2 years, 18% chance they survive 3 years, and so on. These sum to 100, because that's all possibilities. So these sum to 1.00. And then we want to know what is the average survival time? What is the standard deviation? What is the probability a person survives more than 2 years? And then what is the probability that survival is more than one standard deviation from the mean? Okay, well, first we got to find mean standard deviation. So we want to do a table for this data. So we're going to do this extension table, x, probability of x, x times probability of x, and then x squared times probability of x. So we've got here 1, 2, 3, 4, 5, 6. Probabilities were 0.35, 0.22, 0.18, 0.15, 0.06, and 0.04. And then to get the third column, you multiply straight across. So 1 times 0.35 is 0.35. 2 times 0.22, 0.44. 3 times 0.18. If you do the calculator work there, you get 0.54. 4 times 0.15 is 0.6. 5 times 0.06 is 0.3. And 6 times 0.04 is 0.24. And then we're going to total stuff down here. Your probabilities here should sum up to 1. The total on this column with the calculator work, 2.47. And then x squared times the probability. So 1 squared is 1 times 0.35. So this is 1 squared times 0.35 is 0.35. Next one, 2 squared times 0.22. So that's 4 times 0.22 is 0.88. 3 squared, 9 times 0.18 is 1.62. 4 squared is 16 times 0.15 is 2.4. 5 squared is 25 times 0.06 is 1.5. And then 6 squared is 36 times 0.04 is 1.44. And then if you sum those up, you'll get 8.19. And then our mean of the distribution is the sum of the x times probability of x column. So that's right here, 2.47. So that's the answer to A, 2.47. That's 2.47 years. standard deviation for the distribution. So remember that sigma squared is that last column, sum of x squared p of x. And then you subtract off the mean squared. So in our case, it's the 8.19. And we are subtracting the 2.47 squared. And that will give you 2.089. And that's the variance, sigma squared. And then your standard deviation, you do square root 2.089. And that will give you 1.45 to 2 decimal places. So that's standard deviation right there. Probability a random transplant will survive more than 2 years. So for part C here, so this is A, this is B. So probability that the survival time x is greater than 2. So, well, if x is greater than 2, then it's 3, 4, 5, or 6. Or it might be a little bit easier to do the complement, 1 minus probability that x is less than equal to. Because that would be 1 minus x less than equal to would be 1 or 2. So 0.35 and 0.22. And that will give you 0.43. And then more than one standard deviation from the mean. So part D, this is asking what's the probability that your x value here in the middle is between the mean, mu, more than one standard deviation from the mean. So let me draw a picture here. So we've got our mean in the middle here. If you add one standard deviation, you've got mu plus sigma. If you subtract it, you've got mu minus sigma. So we want to know what's the probability that x is out here, more than one standard deviation on the right, or out here, more than one away on the left. So this will be probability that x is greater than mu plus sigma, or plus probability that x is less than mu minus sigma. So let's see here. Mean is 2.47, standard deviation 1.45. So this would be probability x is greater than 2.47 plus 1.45, or plus probability x is less than 2.47 minus 1.45. Give myself a little bit more room here. So this is probability x is greater than 2.47 plus 1.45 is 3.92, plus probability x is less than 2.47 minus 1.45 is 1.02. So if you're greater than 3.92, we look at these values. The ones that are greater than 3.92 are 4, 5, and 6. So this would equal probability that x equals 4, 5, 6, plus probability, if x is less than 1.02, there's only one x value that's less than 1.02, 1. So 1. So we'll take probability of 1 and then add it with probability of 456. So 4.15 plus 5.06 plus 6.04, and then plus probability of 1, 0.35. So that's 35, 45, 50, 60, so 0.60. Now, ones that we had done before, it was instead of more than one standard deviation, this is more than one standard deviation away. If it said less than one standard deviation away, then you would want this stuff in here. So then it would be between 1.02 and 3.92 instead of past the 3.92 and past the 1.02 with a 2.47 in the middle. So it depends on which way they ask that one. Number 7, determine if the experiment is binomial. So NASA's determined there's a 0.05 chance, 0.05% chance that the booster system fails on a particular model. 100 boosters are sampled and tested. So number 1, we've got a fixed number of trials. Yes. So n equals 100 is a fixed number of trials. Only 2 outcomes. The booster either works or it fails. Nothing in between. Thirdly, probability of failure, which is what we're interested in, because we want to know, here it says 0.05% chance the booster system will fail. So that's how we know we're interested in failures. Well, if it works, we're great. We love that. If it fails, we're really concerned. So if a booster fails. So probability of failure for any booster is 0.05%, which is 0.0005, because percent, you move it 2 to the left. And this is the same for all trials. So that checks out. And then the fourth one is that trials are independent. So one booster failure should have no effect on the others. At least we're not given any indication that it would. So yes, this is binomial. Satisfies all 4 conditions. So if one of these conditions fails, then it's not binomial. And then our last question here, practicing with some binomial probabilities. Prevalence of diabetes in a certain population is 40%. That is our P. So a quote-unquote success is person has diabetes. Suppose we sample 10 individuals. So that's going to be our sample size. So n equals 10. And then we want to compute the probability that at most 3 will have diabetes. So that's saying the probability that x is less than or equal to 3. And then we can use the the distribution function on your calculator to do this. So binom CDF is cumulative. So we want binom CDF. And the syntax for that, go to second distribution. Binom CDF, remember, is off the bottom. PDF is if you want one probability. CDF is everything up to the value you enter. So we're gonna enter there. Trials are 10. P-value 0.4. And then our x value less than equal 3. And paste. So binom CDF 10.43. So 10.4 and 3. That's n, p, and the x. And the CDF gives less than equal probabilities. So you have to write everything as a less than equal. So, and let's go ahead and compute that. 0.382283823. Usually do 4 decimal places. At least 2, but less than 6. So this is probability at least 2. So x is going to be between 2 and 6. At least 2 would be x greater than equal 2, but less than 6. So that's going to be 2, 3, 4, and 5. And remember, what we have to do is we have to write this in terms of less than equal probabilities. So we could do less than equal 5 and then subtract off less than equal 1, because less than equal 5 would be 0 to 5, subtract off 0 to 1. So we could write probability x less than equal 5 minus probability x is less than equal 1. So this is 0, 1, up to 5, and we subtract off 0, 1, and that's going to leave our 2 to 5. So this will be our binom CDF again. So let me just copy that. So 10 trials, P is 0.4, but now our X is going to be 5 minus, and then we're doing 0 to 1. So then our X on the end there is going to be 1. So let's go ahead and do that on the calculator. So I'm just going to do second enter to pull up my previous calculation. Just going to go back and overtype that 3 with a 5, and then hit a minus sign, and then do second enter again. Wait a minute. I hit something wrong here. Let's clear that out. Second enter. I think I needed to have that highlighted. So there we go. So I want a 5 there. And then let's see, minus. Let's go up and highlight that again. I'm going to press enter. And I want a 1. Now you can just go through the menu twice. But I'm just trying to save time in the typing. So I did 8337 and then minus this one, 7847. All right, and then exactly 4. That's probability that x equals 4. That one's going to be binomial PDF. So binom PDF. 10 trials, 0.4 is P, and x equals 4. So for equal probabilities, that's when you use PDF. So go back here. Let's clear this out. Second distribution. PDF 10.6 4.1115. Oops, I want 10.4. Sorry about that. So I want 0.4. There we go. 2508. And then mean and standard deviation. So this is binomial. For binomial, mean is just n times p. There were 10 trials, and p is 0.4. So 10 times 0.4 is 4. And then your standard deviation is square root of np1 minus p. So that's going to be square root of 10 times 0.4, and then 1 minus 0.4 is 0.6. We'll go ahead and compute that. So second square root, 10 times 0.4 times 0.6, 1.55. And there we have it.